they found a characterization for this in terms of finite combinatorics. So I will phrase it in sort of more modern terminology. So this is simply omega times the following number. Sorry. So this is the least number of vertices of a directed graph. So directed graph meaning you have either no edge or an edge which has a direction between any two vertices, such that you either have an independent set of size m or you have a transitive subtournament of size n. This means you have a complete subgraph and the direction of the arrows correspond to an ordering of the vertices. So, and what I looked at some time ago was the same for finite multiples of omega squared. So this means you're looking for homogeneous sets which are finite copies of omega squared. Omega squared means you have basically natural numbers, many copies of the natural numbers, one stacked after the other. Or you can say it's sort of the order type of pairs of natural numbers lexicographically ordered. So, and you end up with a similar characterization which is sort of involved, which is basically this, where an corresponds to a subtournament in which, okay, so you have a digraph. So you have between any two vertices either an arrow or not an arrow. And if you have an arrow, it has one of three colors. And this is the least number of vertices which you need, such that regardless of the way you're doing this, you either end up with an independent set of size m or a transitive subtournament of size n, where any triple is in this list. So now the reason for this is probably, okay, how much time do I have left actually?
3 minutes.
3 minutes, oh that's good. Okay, so I'll try to quickly give an idea about the reason. So basically what you care about is the color of a pair where one point lies in one omega square block and one point lies in the other. So then basically two natural numbers distinguish your, describe the relation of these points. So you can apply Ramsey's theorem to basically make the coloring canonical, so that the color only depends on how these coordinates behave to each other. And then you have basically one pair of coordinates and one pair of coordinates, and you have these three possibilities. So this should be ascending order in the natural numbers. So they can look like this, or like this, or like this. And this gives you basically sort of 6 possibilities, but with a symmetry. So you have a directed graph, and you have an edge, and it has, so you have a direction, and you have one of 3 colors. So what is the problem? So an upper bound, if you set n equals 3, then we know that we have a quadratic upper bound for the normal Ramsey numbers. And you can actually prove for this kind of Ramsey numbers also a quadratic upper bound. So R of Im L3 is at most n squared. And I also looked at upper bounds for this, but the best thing, considering this finite description of the problem, and using a degree argument, basically, the best I could prove is that R of Im, A3 is basically cubic. So let me see whether, okay, I think I can remember it. So it's 2m plus 1, m squared plus 4m minus 6 over 3. Anyhow, so something cubic. And yeah, I don't have better lower bounds. So basically, there's a whole gap in our knowledge about the growth behavior of this between quadratic and cubic. And since I'm not really trained as in finite combinatorics, I know basically the idea behind the probabilistic method, but nothing more than the idea. I think it's quite probable that people who are more educated in that field can say something about that. And I actually would be interested, and yeah, hopefully some other people. So that's it, and I'm open for question if I still have time. So. Yep. Okay.
So Jan Wolek, please.
Oh, sorry. Oh, sorry. I should say I have, for anyone who's interested, some reprints of the article. Okay.
Does it work? Yeah, okay. Yes, so my name is Jan Volec.
Sorry.
That's fine. The Czech way of pronouncing it. And okay, here is my email. And the problem I would like to post is about monotone subsequences in permutations. So before I state the problem itself, let me, in 1 minute, recall the theorem of R' and sec'. So it's maybe not the unique way how to say what R' sec', one of R' sec' theorems say. But one way of saying is that if you give me a permutation pi, on k minus 1 squared plus 1 points, then it contains monotone subpermutation of length k. And what do I mean by subpermutation? I mean, so a subpermutation. Maybe let me first show you an example that I prepared. So if my permutation pi would be 2, 1, 4, 6, 3, 5, then I can imagine that that I draw 6 times 6 square. Then I fill the square according to my permutation. So in the first column I put 2, then 1, 4, 6, 3, and 5. And subpermutation would be just a cell. Let's say that a particular subpermutation would be, for example, this one. I choose some columns, not necessarily consecutive, and I look at the subpermutation induced. I look at the pattern that is induced by those columns. So, for example, this would be one subpermutation of length 3 that is monotone increasing. Okay. So I know that when my permutation has at least this many points, I at least contain one monotone subsequence, one monotone subpermutation of length k. And now, so the question I would like to ask is how many monotone subpermutation of length k a permutation pi necessarily has to contain. So fix k and let pi be permutation on n points. How many monotone subpermutations of length k pi needs to contain. And the regime I would like to think is that I imagine that this n is is very large, or that this n is tending to infinity. So r dash sec dash tells me, okay, that it has to contain at least one, or even if I do a little bit, if I think it a little bit more through, it gives me that there has to be some positive proportion, so it has to be at least some c times n choose k plus some low order term, and I wonder what this c is. So how much time do I have now? Minus a minute?
1 minute.
Okay. So let me just say that if k is equal to 3, then essentially this can be related to the Goodman's theorem on triangles and independences of size 3 in graphs, and the answer is 1/4. If k is equal to 4, we know that the answer is 1/27, and in general, we believe that the answer should be 1/k minus 1 to k minus 1. And what should be the construct? What should be the extremal construction? If let's say that k is equal to 3, I split my square representing the permutation into k minus 1 part, and inside this part I put a monotone decreasing permutation, and here I put monotone decreasing permutation, or I can take the reverse. So if I haven't messed it up, those should be the two pictures for k equals 3. And for general k, I would divide it into k minus 1 parts and do the similar picture. And then, so now you probably see where this k minus 1 to k minus 1 comes from. Okay.
Okay. So sometimes we come up with good open problems, sometimes we just steal them. So I'm going to present a problem which, well, basically it's a problem of Boris Spook, but then I'm going to ask a couple more things afterwards, which are related, but...
Please start by writing your name.
Yeah. Yeah. They're Fs, right? Fs. Okay. So maybe I should. I don't know. Has everyone got that stuff down? Maybe I should start over here or something. Okay. So I'll start with the problem that Boris Spook posed. So it's related to taking, well, we know people study the chromatic number of graphs. He was saying, start with the graph, take a random subgraph. How can you relate the chromatic number to the chromatic number of the original graph? So I guess you could start by saying, we'll have some notation for a random subgraph of a graph. So given G, a graph, and P in 0, 1, let GP be obtained by keeping each edge with probability P. So of course, all independently. And so Boris was sort of asking, we start with the graph, it's maybe got quite a lot of edges, maybe it has quite a high chromatic number. When you do this procedure of going to a random subgraph, can the chromatic number suddenly fall dramatically? So can chi of GP be much, much smaller than the original chromatic number? So given that we've started with some fixed graph and it probably has a fixed number of vertices, maybe the right way to talk about it is actually look at the expected number of the expected value of the chromatic number. So he can prove, for example, if you take P as a half, so Boris can prove that the expected value of the chromatic number of G a half is at least the square root of the chromatic number. He does some trick about a graph and its complement, and you can get the chromatic number of a graph. Yeah, anyway. But he conjectures, so I'm going to go through this quite quickly, obviously, for obvious reasons. He conjectures that it's actually more like at least some constant chi over log chi, which I think is a very nice problem. So I should say there exists C bigger than 0, such that holds in general. And I tried to think a bit about that problem. This is quite a few years ago, but I thought about it a bit, and I thought, well, when you think about chromatic number, you start, I mean, each color class is an independent set. You start thinking about independent sets. We're supposed to know more about independent sets, I guess, especially this guy. So what is there some sort of form of the problem just in terms of the size of independent sets? So you could say, as a question, does there exist a constant such that the expected value of the independence number of GP is at most this large constant times, so the independence number of the original graph maybe times this log of the chromatic number. But once you've changed to this setting, this is a problem about chromatic number, this one isn't especially, then it's maybe slightly odd we have in terms of the chromatic number here. And what you could say is a stronger question than this, a stronger thing to ask. We know the chromatic number is always at least the clique number. So maybe you could have the same thing also being true for the clique number. The size of the largest clique in the graph. So I can't give a full justification of why I believe that should be true. I can give a justification for why the clique number is a relevant thing to consider. Sometimes when you're saying, well, is this going to end up being an independent set when you take this random subgraph? You know, in the original graph, your independent sets had some smaller size alpha. Can it go up to a much bigger size? Well, one way of estimating that is to say how many edges do I need to get rid of when I do the randomness. And that would be related to just sort of applying Turan's theorem, say, within this set. Well, if you happen to have a very small clique number, then you'd know actually you could force more edges than you could get out of Turan. So I mean, it's just sort of justifying that some relation to the clique number is perhaps going to exist. And I mean, it's worth noticing as well that, I mean, if this is true, then if you take a graph with, say, triangle-free graph or graph with bounded cliques, then this is asking whether your independent set size only goes up by a constant multiple. So yeah, that's basically the type of thing. Any questions on that?
Have you thought about reducing the numbers? I mean,
I don't think they're strictly equivalent. I mean, I think there'd be more work to do. I think if you did this one, yeah, I don't know about an equivalence. So obviously they're related in the sense that if you wanted to bound the chromatic number, you might start by saying, well, the largest independent set hasn't gone up by that much, and yeah, we're done. We're done. Yeah, we're done.
All right. You hear me? Yeah? Good. The problem I'm going to present... Yes. Okay. So the problem I'm going to present is on a variation of the Cantor argument to prove the existence of transcendental numbers. All right, so first, right. All right, I think that's yeah. Okay, so who knows the Cantor diagonal argument in number theory? Okay, so that's good. But I'm going to show a variation. So if you have to teach at some point a number theory class, it might be interesting to actually just know the existence of this fact. So what Cantor did is actually he just thought, okay, I know that the algebraic numbers are countable, so I can just write them. So let's say we restrict to the numbers between 0 and 1, and then I write the first one, so I write it, let's say, in base 2. Okay, so I write the first one, A11, A12, A13, like this, in an infinite tableau. And then I write the second one, A21, A22, A23, and so on. And then once I'm done, eventually what I do is I create a new number, tau, in this way. So I'm going to create this number 0, 11 bar 1 A11 bar A22 bar and so on, where AII bar is simply equal to AII plus 1 mod 2. All right? And so this number, the claim is this number is not in the tableau. All right? And then you prove that basically this number is transcendental. It cannot be in the list. All right? But actually the fact is the following, that actually, let's say, pi 0, A11, A22, dot, 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 is also transcendental. Okay, so this was actually proved in 94 by Gray. So this is 94. So actually the argument is quite just combinatorial. You just have to check it out. I'm not going to do it, so if you're interested, just ask me after. And this was also reproved a little bit later by
What was proved?
this line. So actually it should be written like this, and then this here.
Always?
Seems, yeah,
Only, I don't know. Maybe it was proven before, but it seems that it was not noted before. Roubaix.
Any assumption?
No.
Could you spell out the theorem?
Pi equals 0 dot the diagonal is also transcendental number. Of this tableau, basically.
What is this tableau?
Algebraic numbers between 0 and 1, counted in some manner, whatever.
Yeah. That's the counter argument. You list their countable numbers, so you just enumerate them in some way, your favorite one, and then Cantor's argument was about tau, but actually you can just do it with pi, the actual diagonal.
Why is there some one?
Hmm?
Somebody asked in the back, and it seems correct. No?
Yes,
Why isn't tau plus pi 1?
yes,
Somebody asked it, I didn't know who it was.
fine.
Fine, yeah.
Yeah, they sum to 1, yes.
Yes.
Yeah, can be. Can be.
Yes. It's a very easy theorem, as you know.
Okay, maybe. Well, it's an easy theorem, but that's not the point of the open problem. Anyways, so you now you know the variation. That's just the first thing. That's actually not the point of the problem. So here's the beginning of the problem I want to present. So assume now. Just want to hurry up and present you the problem. So assume now that, let's say this was T, like an infinite matrix. Right? Assume now that T is a finite tableau. So square tableau of size n times n. Okay, and this argument actually tells you, if you look at the following two sets, so R L of T for the lines to be just the set of sequences given by the rows of T, and then P of T to be the set of diagonals obtained by permuting the rows of T. Okay? You take these two sets and then definition. Oops, sorry. T is called Cantorian if P of T intersected with L of T is empty. Let's do an example. Two by two tableau first. Is this Cantorian? So the set of rows is 0, 1 and 1, 0, and the diagonals are 0, 0 and 1, 1. Therefore, it's Cantorian. Okay, and then this one, 0, 1, 0, 0, 0, 1, 1, 1, 1, 1. Is it Cantorian? Yeah, exactly. Okay, quite easy. Then,
Is it your definition, Cantorian?
no. These guys. And that's actually these guys that presented this problem. So, set Cn2. 2 represents the basis, because actually you can ask the question in any basis, but in this case, let's just say base 2. So set this to be the number of Cantorian tableaus of size n times n in basis 2. All right. Then in another paper, Mendes France showed the following. And right after is the problem in 2007. You have the following bound on Cn2 plus little over 1 times n squared. So you have at least this number of Cantorian tableaus. Yes. Yes, yes. Problem. Find the following limit when n tends to infinity of the following ratio, log of NCN over the log of 2 to the n squared, if it exists. That's it. So it's not known, apparently. So up to you.
I think I don't need that.
For the recorder, yes.
Okay.
Let me erase and then put this.
Thanks. Well, I have two problems. First, chromatic number of ball packings in dimension D asymptotically. So a ball packing means a set of balls with disjoint interiors. And here I can say the balls are all unit balls to make the problem easier. And the upper bound is the one side casing number plus 1. This is very easy. If you don't know the proof later. And the lower bound, a trivial one is D plus 1. Because you can use just put a ball at every vertex of a simplex. And this is trivial, but it's written down by in 2012. In this paper, they formally asked this question as a generalization of four-color problem. Because in dimension 3, disk packings is just a planar graph. And
in fact, before them, there is a non-trivial construction of lower bound gives d plus 2, which uses a spindle. Their construction is just in dimension 2, but it's easily generalized to any dimension. It's 5 years ago already there is a non-trivial construction. And there is a d plus 3 construction, which used halved cubes. Tom is spindle, and this one is by Maillard. And this one is by Cantwell on mass overflow. So this is in 2009, and I believe the current bound should be this by strongly regular graphs. Actually, it's 2 days ago by me, and conjecture. The lower bound should be something like exponential to the square of dimension. Because all these bounds, they are trivial, and they are not trivial, but slightly better than linear. And there is a this one-side Casey number is exponential, almost exponential. So, and we expect some proof similar to the proof of Carlyle and Kahn to the Boswell conjecture that disproves the Boswell conjecture, because as Boswell conjecture asks for the chromatic number of the maximum distance graph, because in that case every point has maximum distance 1. And this problem asks for when the minimum distance is 1, what is the chromatic number? So this is just the opposite of Boswell conjecture. So that's problem 1. And did you note that down? Late. So problem 2. Can every polytope, d-dimensional polytope, be realized such that all vertices disjoint from an interior of a sphere, and all facets intersect the sphere. So you can replace vertices by any I-dimensional faces, and facets by any d minus j dimensional faces. So the motivation is describing problem. So we know that 3-dimensional polytope can be realized that such that every one face, every edge is tangent to a sphere. And for any other dimension and dimension for the faces, you have some d-dimensional polytope that cannot be realized such that every k-dimensional face is tangent to a sphere. But tangency is quite a very strong condition. So if we lose the condition, we just ask for disjoint from the, so every vertex is outside the sphere, and every facet intersect the sphere. Can it be always realizable? Yes. That's the two problems.
Okay, I will ask two questions about the existence of sparse combinatorial objects. So let me start with the conjecture of R dash. There is a term here that I need to define for you. There exist Steiner triple systems. I hope by now you know what that is, with arbitrarily high girth. So I will not dwell on this, because even if you didn't hear this series of talks by Peter Kivash, I'm actually going to speak about something easier that I'm going to mention. So the main thing that I want to define for this is what is meant by girth here. So this is a 3 uniform hypergraph. And how do you quantify what girth is? So think about what girth in graph means. You take a vertex, there are these vertices, and you keep going, and each time you discover new edges at the cost of a new vertex. And then all of a sudden, there is an edge coming in for which you didn't have to pay with the vertex. So the girth of a graph is the smallest v such that there exists a v configuration. These are vertices, and these are edges. That's the usual definition of girth in graphs. And here you want to do a similar consideration. You start with this face, and it's a Steiner triple system, so no edge is covered twice. So you go like this, and this is a face, and this is a face, and this is a face, and so on. And you continue each time you create, let's say, this is a face. In a complete analogy, you get a new face for the cost of a new vertex. So, and then all of a sudden, let's say you discover that this, and perhaps this guy are a face, and you got a face without paying for a vertex. So the definition then is the girth is the minimum v, at least 4, such that there exists a VV minus 2 configuration. These are vertices, and these are faces. So that's the notion of sparsity that I'm talking about. And so Erdős conjectured that you can have a Steiner triple system with arbitrarily large girth. The situation of this problem is very bad. I will not go into this, but it's despite the great appeal of Erdős problems and the fact that this has been open for 40 years, we are very far from understanding anything about this. So I'm asking a much easier question. So now you can understand this even if you don't know what the Steiner triple system is. So easier question or problem. Does there exist an absolute constant C and 3 uniform n-vertex hypergraphs with at least C n squared faces and arbitrarily large girth? So in the Erdős problem, in a Steiner triple system, there are n squared over 6, about n squared over 6. He speaks about C equals 1 over 6. And so I'm happy with C, which is 1 over 100.
No edge is covered twice.
Right, that's in particular included here, because that would give you 4 vertices that contain 2 faces. So no VV minus 2 configuration for V up to G. That's the target. How am I doing on time?
2 minutes.
2 minutes. Okay. So that's one notion of sparsity that I'm interested in. Very curious. There are reasons to think that the answer is yes, and there are reasons to think that the answer is no. I'm not even sure what to conjecture. Just for those who know I remind you that evidence against it perhaps is the 6-3. It doesn't prove anything, but the 6-3 theorem of Ruja and Semeredy is perhaps some evidence, perhaps for a negative answer. So question 2. So think of a Latin square. If you don't know this, then take this as your definition. It's an n by n by n array of zeros and ones in which every line has zeros and ones. Every line has exactly 1, 1. So it's a higher two-dimensional analog of a permutation matrix. If you never saw this, never mind. That's your definition. Lines, there are 3 types of lines. There is row, there is column, and there is a shaft. Okay? How sparse can such a thing be? So I'm looking at a k by k by k subarray of this. And there are 2 obvious things. Very easily, I can find such things with at least k1s in them. In the same way that in a permutation matrix, if I give you a k by k, you tell me k, I can find a k by k submatrix that has k1s in it. So there are at least k's. Also, the density of 1s here is 1 over n. So also in particular, there must be something with at least k cubed over n. These 2 numbers become equal at k equals root n. So now I can ask the question, does there exist an order n Latin square such that in every root n by root n by root n subarray, so there are only O tilde of root n ones. The tilde says that if it's root n times log n, I'm still happy with it. But ideally, perhaps even this, and again, I don't know. So can such an array be as sparse as, except for the obvious things, it's no denser than that in the ones. That's it? So if people want to volunteer questions, it's still okay, but you're still under the 5 minutes restriction. Anyone, please?
Thank you. Hello?
You can start here.
Good. So this is going to be a problem with a slightly topological character. Oh, yeah. So I have a quote. And this is my email address. Okay, so here's the problem. So S1 will denote the unit circle. In R2. And now we take some subset of the closed interval going from -1 to +1, and we think of this as a set of forbidden inner products. Forbidden inner products. Okay. I'll use lambda to be the Lebesgue measure on the unit circle. And I'll always normalize so that the whole circle gets measure 1. Right. And so in a lot of my work, I'm interested in the following number. So given some set x, we're interested in the supremum taken over all. Okay, let me say it like this. So what I'll do is, so given this set x, what I'll do is I'll define a graph. So the graph will be this. Graph. Where my vertex set will be the unit circle. And what I'll do is I'll put an edge between 2 points when they lie at a forbidden inner product. So so this will be the set of pairs of points such that the inner product lies inside the forbidden set. Okay, and that makes this definition easier. So this alpha x will be the supremum of measures of independent sets. And of course, we require those sets to be measurable. Okay. So here's maybe the simplest example. How am I doing for time? 2 minutes. 2 minutes, good. Perfect. Okay, so this is probably the simplest example. So I'll put one forbidden inner product. Okay. So what can I do? I can take an open arc of length 1/4 and all the antipodes. Okay, and this is a set. No 2 points in this set will make inner product 0. And how much of the circle have I got? I've got a half. And in fact, it's not too hard to show using an argument actually quite similar to what Wojtek did. One of the things Wojtek did this morning. You can get equality. And it's a fact that if I've got some finite subset of the circle, I'll take some finite subset of the circle, then alpha of x will be no more than the independent number. X is my forbidden inner product set. Okay. This will be no more than the independent number of the graph induced on this finite set of vertices F divided by the size of F. Okay. This is not too hard to prove. This is a simple averaging argument. And now I can state the question. Okay, that also shows this is best possible, by the way. Why? Because I have one edge. So the question will be, does there always exist finite f such that alpha x is equal to the independence number of this induced subgraph divided by f. Okay, so we have a way to get upper bounds on this alpha x. Just look at finite subgraph. And so the question is, can I always find the exact number with some subgraph? And that's the question. Okay. It's not. I can tell you that it's not true in general. Yeah. If I have time, I can say more about what's known, but I think I'm probably finished. Okay. So if you want to know more about it, talk to me.
So my name is Avraham Morgenstern. And I want to ask a question about directed graphs. So a directed graph is a simple directed graph, no loops, no multiple edges. So I'll state a theorem. So the sum of the squares of the out degrees of the graph. Okay, so let's write where. So that's for every directed graph G. Degree of V is the number of outgoing edges. And the theorem states that the sum of squares of out degrees is at least 3 times the number of cyclic triples. So C is number of cyclic triples.
This is comparative.
Yeah. So this is first Coparty V and Rosman, and later Rosman Coparty. I don't want to tell you I could tell you the proof in less than 5 minutes, but whenever I tell this problem to people, they tell me, why did you tell us the proof? Now we can't solve the problem, so I won't tell the proof. I'll state the conjecture. So actually my first challenge to you is just to find a new proof for this, maybe a different proof, because the old proof, the known proof does not generalize well to other situations. So, but my conjecture is stronger. So I claim that the sum of squares of out degrees is at least 3 times the number of cyclic triangles plus 1 time the number of transitive triangles. This is a transitive triangle. Okay. Question? For every directed graph, for every directed graph G, I claim that this inequality holds. So it was first 2006 by V and Rosman, I think, and later 2012, I think, by Rosman and Coparty.
So this is a strengthening. Okay. Okay, so I want to publicize an open problem. So this is an open problem in model theory, but it's actually a problem in combinatorics. In a paper of Herwig and Laskar from it's pretty old, it's from the last millennium. So this is the conjecture that for every finite tournament you can find a bigger tournament to embed it in. So there exists a tournament which has the property that every partial automorphism of T extends to a full automorphism of T prime. So I'm going to explain everything, but I'll just write it first. Automorphism of T extends to a full, because this is just a concept of automorphism of T prime. Okay, so what is a tournament? A tournament is just you take the complete graph and you orient the edge in some way. So for example, and so you think about this as, let's say, players, and each pair plays and one of them wins. So this is why it's called a tournament. And what is a partial automorphism? So you take just two sub-tournaments which are isomorphic. For example, any tournament on two elements are isomorphic. And you have this partial automorphism. And usually there is no reason for a partial automorphism to extend to a full automorphism. For example, here I have a partial automorphism, but if I take this element and the element that corresponds to it, then it might be that one of them has an outer degree which is bigger than the other one, so there can't be a full automorphism taking this to this. But maybe if you enlarge the tournament, then you can suddenly extend all of these partial automorphisms. So I'll just tell a little bit about the history of the problem. So the first result, so actually you can ask it about all kinds of structures, not just about tournaments. So Udi Horoshovsky, he proved it for just for graphs. Just undirect graphs. And then Herwig proved it for hypergraphs. And also for triangle-free graphs. So you can ask it for any class of models. And Herwig and Laskar, in this paper, they proved the strongest form that is known, which is just any kind of structures with several relations, which is, so I'll just write it here. Herwig and Laskar, they proved it for F3 relational structures. So yes, but tournament, they don't fit into this into this class because, well, you can say that tournament is a graph which is free of this, let's say, and this, but then you cannot force that between any two vertices there would be an edge. So I think this is a nice question.
Okay. Oh, could you hear me? Okay. Okay. Okay, so, oh yeah, my name, yeah. Right. Okay, so let QD be the d-dimensional hypercube. Okay, so, yeah, so as usual. So now let t at least 4 be even, and let H be a subgraph of QD, well, a spanning subgraph, so it's got the same vertex set. So the question, okay, I'll say, so definition, H is CT saturated if H doesn't contain a copy of CT, but if I add an edge, so H plus E contains CT for all of the possible edges I could add. But so what I mean is for all edges in QD minus E of H. Okay, so right, so it's got no cycle of length T, but if you increase the edge set, you all of a sudden get a cycle effect of length T. Okay, so the question, what is the minimum number of edges such that you have a saturated graph? So that's the question. So yeah. So if you could, you'd also want to know what are the tight examples, things like that. So of course, I mean, if I change this minimum to a maximum, then what I get is it's like a Turan problem for even cycles in the hypercube. But this is kind of sort of a dual problem to that, where you're minimizing instead of maximizing. So, yeah. So, I guess a guess would be, maybe a linear in the number of vertices, perhaps. So if you changed, instead of doing cycle saturated with respect to cycles, if it was saturated with respect to small hypercubes, then then we know that this is the answer. But for cycles. Oh, no, there should be, so yeah, so I'm seeing, like, so t is constant. So I'm just, yeah.
So you know how to do it for triangle, for example?
No,
it's,
bipartite graph.
yeah, the hypercube is bipartite, yeah.
Squares. You know how to do it for squares, and it's not.
Oh, right, so actually, yeah, so actually, so that, this works for, yeah, it's true for t equals 4, because actually the right, so if I change, so if we change ct for qm or qt, you know, then actually that's the right order of magnitude, and q2 is equal to c4.
Okay, so the first case that isn't, that you can do.
Yeah, the first case,
So
so,
equals 6.
right, so 6 cycles, I don't know. Yeah. So we haven't really thought a lot about the question, but yeah. All right.
Okay. So my name is Clara Schickelman. And the question I want to ask, like there's interesting phenomena that I want to show and ask about. So generally, if we're thinking about Turan-type problems, so usually we'll define x and h to be how many edges can you have on n vertices without getting a copy of h. And we know that this is determined by the chromatic number of h plus minus something. So so if we don't want to ask about edges, but about other graphs, so something that one might think about is how many K3s, how many triangles can you have in the graph before you'll get some graph H. So if we're looking at edges and we want to forbid a union of two graphs or a family of two graphs, this will be determined by one of the specific graphs. So if we have some, for example, H1 and H2, and we just don't want to see two disjoint copies, in the case of edges, this is going to be determined by one of them. But if we're looking at triangles, so even if we want, if H is cycles of length 5, then if we just want to forbid one such thing, then this is round n to this power. Okay, so this is this can be proven. But once you don't want to have two disjoint cycles of length 5, you can easily get to, you can take like this to be n, well, you can divide your vertices into two parts, take the complete bipartite graph here, connect them to this one vertex here, and then you get something which is n to the power of 2, and still you don't have two disjoint cycles of length 5, because any cycle of length 5 must use this vertex. So the coloring number is obviously not what you want to look at when you're looking at triangles. And the question I had in mind, or I was even asked, is what is the thing about triangles? What's the important criteria that if you want to look at a bunch of graphs or specific graphs, what's going to be the important criteria? So here it was the chromatic number and what's going to be here. And one idea that came up, not mine, but still, is that it's the size of the second largest color group when you color a graph. but that's a very wild guess. That's I can't stand behind. So, questions?
Everyone, my name is Greg Bodwin. And this is my email. So I'm going to tell you about a short little problem about graph spanners is the name of the object. So we have G, which is undirected and unweighted. And we say that H, which is, I'll say G equals VE. So H is then some subgraph of G on the same vertex set, but a different edge set. We say that this is a plus K spanner. Of G, if this property holds. So for every pair of nodes, we have that essentially H approximately preserves the distance. So is between so the distance between every pair of nodes in H is, or the distance between every pair of nodes in G is preserved in H up to some small additive constant K. That's the condition that we need for H to be a plus K spanner of G. Sometimes people think about the non-constant case, but the problem that I'm going to tell you right now will just assume that K is a constant. So very little is known about these. A lot more is known when the error is multiplicative or maybe mixed between additive and multiplicative. But here's... Yes, E prime will be a subset of E. So it needs to be a subgraph. So what do we know? We have, if we want K to be 2, then this can be done in O of n to the 3 halves edges. So we can make this claim if we're willing to let E prime get up to, I guess, exactly this n to the 3 halves edges, then we can guarantee that we can make ourselves a plus 2 spanner given this edge bound. It's the number of vertices of both G and H. They're on the same vertex set. Right, so for any graph G, you can definitely make a plus 2 spanner of G, which has this number of edges. And in fact, this is tight, that's known. This is from Ingworth. If you want to do plus 4, we have this and the 7/5, and that's from Chechik. And if you want to do plus 6, then we have n to the 4/3. That's from Botswana. And anything below this is open. This progress suddenly ends right here. So open on some smaller number of edges here. So this is one open problem, and this has attracted a lot of attention, and progress is sort of stalled here for a very long time. So maybe this is hard. So this is one thing you could think about. Another maybe more accessible open problem would be to try and improve our lower bounds. So for this case right here, the lower bound is +4. And so it's sort of, if we look at patterns that we've noticed in other sorts of spanners, it seems like maybe this upper bound can be improved from +6 to +4 in some way. But it's unclear. It would be sort of major progress in an interesting way to close this gap right here in some way. That's all.
Significant improvement in the problem if you restrict to some interesting family of graphs. Suppose you don't ask for general graphs, some special property graphs. Can you do better things?
Random graphs, this becomes quite easy. You can get, I think, n log n edges for any constant. That's all I'm aware of. I think any other restrictions would be interesting progress.